In this video, we're going to discuss some of the structures that go into building a solid. So to begin with, we can have two types of solids. We can have amorphous or crystalline. Amorphous have a whole lot of disorder to them, while crystalline, those are your type A solid structures. They're very structured. They typically have what's called a unit cell, which is the smallest repeating unit of that lattice. Whereas the lattice is a whole bunch of these little bitty building blocks, if you will, that build a bigger 3D design. If you want to, you can think of the unit cell as the individual single Lego, and the lattice is the whole bigger structure at large. And so your crystalline structures, they're going to have a lattice structure like you see here, whereas amorphous structures have a lot more disorder to them. You cannot represent the whole by an individual entity. How do we determine that we had unit cells in lattice or amorphous structures? Well, X-ray diffraction is one of those methods. So just like in Rutherford's experiments, back when we were thinking about the structure of an atom, you had to rely upon tools or experiments in order to confirm the properties of an atom. In this case, what happened is you take an X-ray tube, you shine it at a subject, you'll emit an X-ray beam. And then when that X-ray beam collides with the crystal, it's going to interact depending on where the different atoms, molecules, whatever is making up the crystal, it's going to collide with those, and the image on the photographic plate is going to change based upon where those collisions occurred. And so then basically what's happening is you have these incident rays, which are just simply your X-ray beams. You shine it at the crystal, you know the angle of incident. Depending on where in the lattice it's going to collide with these different points, these atoms, these molecules, it's going to bounce off at a different angle. And so you're able to tell based on the reflected ray where within the lattice these individual points, these molecules or atoms actually coincide. And so this is called X-ray diffraction because the X-ray is diffracted at different angles, but the angle or the phase is going to be dependent upon the location of the individual entity within the unit cell or within the lattice. And so this is the famous equation that has to do with X-ray diffraction. This is called the Bragg's equation. The idea is that because you can know without a doubt the different properties of your X-ray, you know the wavelength, for instance. You can use the angle that is reflected off of the different atoms, and you can use that angle and the known wavelength of the X-ray to predict what is the distance, what's the spacing between the different atoms or molecules within the network. And so this is the equation that gets you there. Now, I will stop to say here for a minute that X-ray crystallography is a very, not tricky, but it's a very big and hard science that I'm obviously not going to ask you to do in general chemistry, but understanding the properties that go into it and the fact that this equation, the X-ray diffraction, is used to figure out these crystal structures, I think is good conceptually as you're thinking through what these crystal structures look like. That being said, there's some really neat work in X-ray crystallography, using X-ray diffraction, using a whole bunch of different techniques together, actually. And a lot of that is like, how do we image a virus? Because if you can understand how a virus is made, you can go and you can work on fighting viruses. You can work on making vaccines for those viruses. But, you know, viruses are tiny little things. And so you can't just look at a virus underneath the microscope, unless it's like Ebola, okay? But most viruses you can't. And so whenever you go, you need to actually image them somehow. And so you can use X-ray crystallography where you crystallize or you attempt to crystallize the virus, and then you're basically using electron microscopy with these principles laid out in our Bragg's equation and in X-ray diffraction. So lots of really cool parts of science are happening every day because of these principles. So here's a picture of what these crystalline solids may look like, and you'll notice that you are going to get different shapes based on what is present at the point of the lattice. And so you might have atomic crystalline solids where you have an atom, like shown here. You've got your diamond. The diamond is just a whole bunch of carbons that are present at the points of the lattice. an ionic structure. So this is salt, sodium chloride. That's where you either have a sodium or a chloride. Notice how they're spaced, where you don't have a sodium next to a sodium in the lattice structure. Instead, it's every other one in a repeating, very consistent lattice structure. And so that's how you get that nice pretty shape that you see here. And then molecular structure. Here's water, where water is present at the points of the crystalline solid. And so there you see a nice pretty snowflake. But the idea still exists that your properties of your crystalline solid are going to exist. They're going to change based on what's existing at that lattice point. So if you have an atomic crystalline solid, an ionic, or a molecular, that lattice point is going to tell you the properties of the solid as a whole. So here's a nice kind of general overview of the different types of solids. So you can have an atomic solid, and then a molecular solid or an ionic solid. But even within atomic solids, there are 3 different types. You have metallic, which is when your atom is a metal. You have your group A atoms, which are going to be your noble gases. Those are going to act very differently than your metals, of course. And then you have your network atoms, and that's where you have non-metals, but they're involved more as a whole, a network as a whole, instead of distinct metal atoms or helium atoms, if you will. Okay. Then you can dig in further and look a little closer at molecular and ionic solids. So within molecular solids, remember you have those strong intramolecular forces within the molecule, but you have relatively weak forces between the molecules. Those could be your dipole-dipole, they could be your induced dipole forces, but either way, compared to the stronger bonds within them, those forces between the molecules are relatively weak. And so you're depending on those weaker forces to hold the layers together, so they're not as strong together. If we compare the distance between atoms compared to the distance between molecules, you can see it's 220 picometers for a P4, a tetraphosphorus molecule, as opposed to 380 picometers between any individual phosphorus of one molecule and the next closest molecule. So there's a big difference there. And then with ionic bonding, you have, yes, those electrostatic forces are holding together oppositely charged ions, and that's true within the entire lattice structure. And so you're going to have your stronger bonding happening there. And so all of these different pieces, whether it be atomic, molecular, or ionic, they're going to build together to help determine the properties for the substance. So whether it be hard, a high or a low melting point, if it's an insulator or a conductor, those different properties are dependent upon what type of substance is at the lattice point, and those substances will determine the intermolecular forces, and all of those go into helping us understand why the solid behaves the way it does. All right, within metallic crystals now, you can actually have very defined, very kind of beautiful packing structures. The idea is sometimes you can have what's called closest packing, where you're trying to pack your metal pieces in as closely as you can. And so how they do that can be one of like a couple different ways. But the idea here is how are they made? Are they made like this top one, the ABAB, where you basically have 2 sheets types and you're alternating in a pattern? Or do you have 3 sheet types where you're alternating? And it depends on what you're trying to build with your metals as to what your structure is going to behave like. So here's kind of another view of it. And then within this closest packing structure, you can have a hexagonal unit cell, or what you see on the bottom is called a face-centered cubic cell, and that's because on each face you have a different molecule or atom, that is centered within that cube. And so the idea still here is you've got different designs, and if we can figure out a model that helps us understand what these different substances look like, then we can predict structures. Am I going to say, okay, here's the substance structure, tell me how it behaves? I'm not in this class. That's another upper division class. But for the sake of this class, just kind of understanding that there is a specific structure that's going to govern how and why substance behaved is an important concept. Here's some more examples of it. So you've got your individual unit cell shown, and then you've got the whole lattice as a whole. All right, so now let's talk about alloys. So alloys are a specific type of that solid substance. So alloys are any time you have a mixture of an element with metallic properties. So it can be where you've got two different types of metals within a lattice structure. And so in this case, you can have two different types of alloys. We'll talk about substitutional alloys first, where substitutional alloys happen whenever you've got the bulk of the lattice structure is made out of one metal type, but then we're going to substitute out some of the copper atoms and we're going to replace them with something of similar size. And so in this case, copper and zinc are kind of similar size within brass. And in order to make brass and have the properties of brass as opposed to just copper or zinc, you mix some of those zincs in and replace some of those coppers. And so what's really neat about alloys is you can get now a substance with a very different set of properties, whether it be melting point or conductivity, but you did that just simply by playing with substituting one metal with another metal of a similar size. The other type of alloy that we're going to talk about is called an interstitial alloy, and this book here by Sam Keene, The Disappearing Spoon, which I really recommend. It's a really fun read. It sounds boring, history of the periodic table, but it's actually fun. He kind of tells stories about all of the elements on the periodic table, so it's a really fun read. And he also has like an audio version, I think, so enjoy. But anyway, interstitial alloy, that is when you've got, instead of substituting out one metal with some other substance that is similar size, you can substitute in a smaller metal or a smaller atom of a different type. And so in this case, we have steel, which could be made with like iron, and then carbon is smaller than iron, and so it fills in the little bitty gaps, the holes in the closest packing structure for iron. And so that's kind of a fun way to see an interstitial alloy. But why I brought up the disappearing spoon was molybdenum. Its role in World War II was explained as an interstitial alloy example. And so that being said, so here, Big Bertha was a German gun, and basically it could throw so many explosives very, very long distance, which would have been really devastating to our troops. But the problem was they needed molybdenum to reinforce the gun barrel, because if you just simply have steel and you got that iron and that carbon, it can get really, really hot if you're going to use that gun over and over and over again in a rapid fire scenario. And so you need some other molecule to sub in and give the metal a different set of properties. And that's the whole purpose of an alloy, is change in random elements in order to give the structure as a whole different properties. So they needed molybdenum to reinforce it. Unfortunately, Germany had no ability to do this, but Colorado here in the States, it was awesome, and there's a company called American Steel that could mine it. And so German, spies basically came over and tried to purchase this, and then they tried, whenever the company refused to sell it to a bunch of random Germans that appeared out of nowhere, they tried to, a little shadier techniques, tried pushing people off of sides of mountains, that kind of thing. But they held off until the very end, and that company was credited for not making it so Big Bertha did more damage than they did with their smaller regeneration rate. So that company really, it was a kind of a neat story that all had to do with people trying to form an alloy that could do its bidding. All right, so that's structure of solids and alloys. And there's a whole lot more that can be said about this. This is kind of an overview. The idea still being that structure determines function. That however the solid is structured, what makes it up is going to tell you what it can be utilized for. And kind of understanding that concept is a very large concept, not only in chemistry, but in biology as well.